engineers. Welcome to another segment of electronic devices, and today we are going to discuss Fermi level. We can say that the Fermi level is the highest energy state that an electron can occupy at the absolute zero temperature, that is 0 Kelvin. In this condition, the electrons occupy the region from the valence band till the Fermi level. The electrons move to the upper energy level with an increase in temperature. Let's consider two temperatures as T1 and T2, which are greater than the absolute zero temperature. Also, T2 is greater than T1. Now, if we start increasing the temperature while it comes to an equivalent of T1, that is, T is equal to T1, we can see that a part of the Fermi level is engrossed towards the conduction band. At this point, if we increase the temperature further and it becomes T2, that is, T is equal to T2, the path becomes wider and a greater number of electrons will be able to move in the conduction band. The Fermi level can be mathematically expressed by the Fermi-Dirac distribution, which is given by Fe is equal to 1 by 1 plus exponential of E minus Ef by kT, where Fe is equal to the probability that a particle has an energy E is equal to energy state occupied by an electron, T is equal to absolute temperature in Kelvin, K is equal to Boltzmann constant, which is also equal to 1.38 into 10 to the power minus 23 joule per Kelvin, and Ef is equal to Fermi level. Now, for different cases of absolute temperature, the position of Fermi level is different. Let's discuss each of these cases. For case 1, at absolute zero temperature, that is, T is equal to 0 Kelvin and E is greater than Ef, putting the values in equation 1, we get E minus Ef by kT is equal to infinity. So exponential of E minus Ef by kT is equal to infinity. Hence, Fe is equal to 1 by 1 plus infinity, which is equal to 0. Hence, the energy level above the Fermi level has no electron. At absolute zero temperature, that is, at T is equal to 0 Kelvin and E is less than Ef, putting the values in equation 1, we get E minus Ef by kT is equal to infinity. So exponential of minus E minus Ef by kT is equal to 0. Hence, Fe is equal to 1 by 1 plus 0 equal to 1. This is our equation 3. Hence, the energy level below the Fermi level has full of electrons. For case 3, when the temperature is increased, that is T is greater than 0 and E is greater than Ef, some electron below the Fermi level Ef will acquire energy and move into states above the Fermi level Ef. For the final case, that is case 4, when the temperature is increased, that is T is greater than 0 and E is equal to Ef, the probability function Fe becomes half. So we can say that the Fermi level Ef is the energy level where the probability of finding the electron is half. The water level at stable position in a beaker can be compared with the Fermi level at the absolute zero temperature. The top of the water level is compared with Fermi level. Water below the top level is compared with full of electrons, and above the water level is compared with the vacant states. Now, the table is shaken. There will be some unstable condition in the beaker and water level will fluctuate. Some water will move above the stable water level and some water will move away below. This can be compared with the Fermi level when the temperature is increased. The position of the Fermi level is in the middle between conduction and valence band in case of intrinsic semiconductor. If the semiconductor is of n-type extrinsic semiconductor, the fill level will shift near the conduction band. If the semiconductor is of p-type extrinsic semiconductor, the fill level will shift near the valence band. In this lecture, we have learned Fermi level definition, Fermi-Dirac distribution, position of Fermi level for different temperature, position of Fermi level in the intrinsic and extrinsic semiconductor. With that, we are at the end of this lecture. We will meet again in another lecture. Thank you and goodbye.